And then we want to bring this all together and say, well, what metabolites are most likely to be generated by my compounds in vivo? Now, this is a really big challenge for in silico methods. If we generate all possible metabolites of a compound, which we can do, this can lead to an overwhelming number of predicted metabolites when we're considering multiple generations. So here I'm showing for dextromethorphan just 2 generations. Here's the drug itself. Here are its direct potential metabolites. And then there's the metabolites of the metabolites. That's 2 generations. And of course, there can be multiple generations formed in vivo. But even if we're just looking at 2 generations, we can see here the green compounds highlighted here are those that are observed experimentally, and they're a tiny proportion of the potential metabolites. And this is a well-known problem for knowledge-based methods for metabolism prediction. We can generate lots and lots of potential metabolites. We can find all the potential metabolites, essentially. But which ones are actually going to be observed experimentally that we need to be concerned about? We actually did an analysis of this for 92 compounds, again, published here in the publication at the bottom. And what we considered all the potential metabolites that could be generated for these enzymes that we are considering here. We actually did correctly identify 96% of the experimentally reported metabolites. In statistical terms, this is 96% sensitivity. But of those generated, only 4% of those were actually reported experimentally. Again, in statistical terms, this is a 4% precision, or another way we can think about it is we're predicting 25 times more metabolites on average than are actually observed experimentally. In fact, it's even worse here for dextromethorphan on the right-hand side. Yes, the sensitivity is 100%. We find all of the experimentally observed metabolites, but the precision is actually 2%. We're generating 50 times more metabolites than are actually observed experimentally. So we can do better than that by using this sort of mechanistic approach to predicting the most likely metabolites, the most likely enzymes and isoforms. Again, let me just quickly demonstrate that to you so you can see what it looks like. I'm going to go back into the software. I'm just going to look at this example for dextromethorphan here that we just saw previously. Going to select the compound here, and I'm actually going to ask it to generate the metabolic pathway for this compound. So this is looking at 2 generations. And again, that will appear very, very quickly. This is actually a very long calculation in practice because it's actually generating many different metabolites and then for each of those metabolites predicting their metabolites. So this can in practice take hours. But again, for convenience, once you've calculated it once, it returns instantly. And what you can then see is, if I just click here, it actually generates a sort of metabolic pathway for dextromethorphan. You can see here a much smaller number of metabolites that are predicted as to be likely to be formed, giving us a much smaller pool to go look at to confirm experimentally. And if I just go back to show you those results in a little bit more detail, what you can see here on the right-hand side is, again, the same color coding. This is dextromethorphan, the drug. Here are the experimentally observed metabolites that are correctly predicted. And you can see that a much greater proportion of those predicted are actually observed experimentally. The precision is increased from 2% to 40% in this particular case. Now, it will vary from compound to compound. The larger, more complex the compound, the harder it is to achieve these very high precisions. But here you can still see in our independent tests a significant improvement in precision over the sort of boil the ocean and generate all possible metabolites. So this can really help to guide metabolite ID experiments to focus on the most likely metabolites, particularly if we need to get into sort of resynthesis of compounds for quantification.